Good morning and welcome to Astronomy 120. This is week 3 of the late start session. Today we are continuing with the basically the topics we started on Monday. We're going to be covering the material related to basically the laws that govern the bodies in the sky, and this is really the start of modern astronomy. Okay, up to this point, we were actually concerned with constellations and things in general. And then at the end, there were some problems with the models we were talking about. I mean, in the old days, people were thinking that the Earth is the center of the solar system. And there is no reason why you would suspect that. I mean, at least on a personal experience. If you go outside, for example, tonight, and you wait for an hour or something, you will see the object shift in the sky by about 15 degrees, okay? They seem to be moving. And if you hang around for a long time, you're going to see them actually track down the stars, and you will see them moving in the night sky. So everything seems to be shifting, with the exception of a few stars. I mean, with the exception of one star, I should say, which is Polaris. Everything else seems to be moving around it. Okay, they seem to be shifting around it. So in this case, hey, especially if you look at it in terms of the sun, for example, it rises from the east and sets in the west on a regular basis. The moon does similar stuff also. It rises from the west and sets, and sometimes rises from the east, but it's always moving the same, basically, dome above us. The planets also do something. Sometimes they move back and forth, and we have justification for that. So that we call the geocentric model, where the Earth is the center of the solar system. Okay. Then we argued, at least Mr. Copernicus argued, that that cannot be true when he looked at the geometry and he was trying to make the case for it. One of his assignments was to fix the calendar and make sure that the calendar fits and everything else, but he immediately basically had to reject the idea that the Earth is the center of the solar system, but rather the sun is. Remember, that argument was made a long time ago before Mr. Copernicus by Aristarchus. But the biggest problem that he ran into was the parallax that he couldn't detect. So therefore, at the end, basically had to be abandoned until Mr. Copernicus, when he looked at everything else combined, he basically when he looked at everything else combined, there is no way that the Earth could be the center of the solar system, but the sun is. So that's basically Mr. Copernicus' view, and he put it in this shell structure, and at the end he came up with better numbers, at least for the period, the time it takes for these planets to go around the sun, and also and also their distance. So those two things were correlated. Then came Mr. Tycho Brahe, who came after that, and he was a wealthy man. He was near basically in the sea between Sweden and basically Denmark, in an island in there. And what he did was he collected a lot of data, a lot of observations. I mean, night after night he would go with no telescope at that time. There was no telescope for him accessible. So basically he would go and track down the object, whether it's Mars, whether it's Venus, whether it's Mercury, whether it's Jupiter, whether it's Saturn. Those are the objects he was tracking in general. And he came up with a lot of data in terms of their position in the sky, in terms of their size, in terms of the time it takes for them to move from location to location to location. And he was able to track them. The moon also, he was able to track he gathered a lot of data, albeit visual, but it's a good, useful data. He was not really a math-inclined person, so he needed somebody to help him decipher that data, but he was protective of that data because it's his. It took him a long time to gather it, and he wanted some recognition at the end for what he did. So he hired a young man at that time who was well known for his math skills, Mr. Kepler, Johann Kepler. And Mr. Kepler was not well-to-do, but he took the job and he wanted to help basically Mr. Tycho Brahe in basically coming up with the interpretation, if you wish. But he didn't really have access to all of the data, so he couldn't do much until Mr. Tycho Brahe passed away. Then at that time, he had access to the data. In doing so, when he had access to all of the data, basically, he came up with immediately 2 laws, and then later on with a 3rd law. And those are known as Kepler's laws. So the first law is, it immediately questions what Mr. Copernicus thought in terms of the path of the planets. Mr. Copernicus thought, and again, this is inherited from before him, that the paths must be circular. No, they're not circular, they're elliptical, he said. If I look at the observation of Tycho Brahe and the data that he collected, the path that the planets take around the sun is not a perfect circle. So that you guys understand what the circle is, you have a central point in here somewhere, and the points that are at the same distance from that center point is what is known as a circle. In other words, to make a circle, all you have to do is make a dot somewhere on the line, and then take a straight line, if you wish, or string or something that doesn't stretch, and run it through. That is how you make a circle. That is not the path of the planet, though. It's an ellipse, and the ellipse is actually a more general form of the circle than a circle is. So what an ellipse does, it has 2 focal points, not just one center. It has 2 focal points. And then you run a string from one focal point to the other focal point and leave it loose. And you run the string, as you stretch it, around. So this ellipse is the collection of points that are at the same distance from 2 points, not just 1 point. So the circle, in a sense, is a special case of an ellipse, because if you take the 2 points and you collapse them on one another, it becomes a circle back again. So the ellipse is more general. One of the characteristics of the ellipse is how elongated it is. It could be very flat, or it could be very close from a circle, or almost a circle. We call that the eccentricity of the ellipse. So that is basically the first law. The first law of Mr. Kepler is, based on the observation of Tycho Brahe, after he refined them, the path of the planets is not a circle, but rather it's an ellipse, where the sun is in one of the focal points. So which focal point the sun is on, it doesn't matter. You just take one, it doesn't matter, okay? The sun happened to be in one of the focal points, that's all, okay? And the other planets, all the planets, they move around the sun in such a way that the sun sits in the focal points of that path. That is law number 1. Of course, that's a problem, because what happened to the idea, the philosophy, the religious belief that circles are the perfect shape? And again, the heavens are perfect because there is no man's sin. And the only reason we have stuff that is messed up in here and we don't have everything perfectly symmetrical is because man's sin. That was a problem, okay, that later on is going to be an issue for somebody else, actually, for Mr. Galileo, okay? So the other problem also, the other law, the second law is that if you take a planet, it doesn't matter which, including Earth, because now we know Earth is actually doing the same thing as it goes around the sun, at least at that time. If you take a planet and you draw an imaginary line between it and the sun, and wait for a specific amount of time, let's say a week, for example, later, or a month, it doesn't matter, okay? Specific fixed amount of time, a day if the planet moves so fast. Okay, you really have to give it a little bit of time, otherwise you're going to have a hard day in motion. So again, let's say a week or 2 weeks, for example, okay? The planet would have moved around the sun during that time. That line, imaginary line, made-up line, that connects the planet to the sun will move in such a way it sweeps an area. So an area now is covered between the old position of the planet and the new position of the planet and the sun. So it's like a triangle, except that there is an arc in it, okay? So that area, it doesn't matter when you do that, as long as you take the fixed amount of time, whether the planet is close from the sun, because it's an ellipse now. Sometimes it's going to be close and sometimes it's going to be far, and sometimes it's going to be in between. So if you are here, it's going to sweep an area in that same amount of time. If you are on the other side, it's going to sweep the same area, regardless of how far it is. So in other words, if it's close, it has to go fast to sweep the same area. If it's far, which is the area in this case needs to be small. I mean, the arc is going to be small because the radius is far away. So depending on the radius, that matters, that plays a major role. So that became the second law of Kepler. The third law took him a little bit of time to really come up with. And the third law really, it's more of a quantitative law. So basically what you do in this case, you take two quantities and you compare them one to the other. So you take the square of the time it takes for it to go once around the planet. That's called the period, okay? For the Earth, it's 1 year. So it goes 1 year, that's a period. For Jupiter, it's about 12 years for Earth. Jupiter goes once around the sun in about 12 years. So we call that a period. For Mars, it's almost 2 years, not exactly, 22 months, okay? So that's basically, for Venus, it's about 7 months. So that is the period. You take that number and you square it. For the Earth, it's 1 squared is 1 squared, okay? For Jupiter, 12 squared is 144. Okay, so that's basically in a nutshell what it is. And for Venus, it requires a little bit of calculation, 7 divided by 12 squared, okay? So that's basically, because it's 7 months divided by 12 months, so it's 7 whatever over 12 year, per year, okay? A fraction of a year, if you wish, okay? Slightly over half a year, slightly over 0.5. Anyway, the point being in here, or is it 8 months? I don't exactly remember the exact number, but the point being in here is you take that and you square it, whatever the square is, okay? Now, you know on average how far the planet is from the sun. The Earth is about 1 astronomical unit, 150 million kilometers, okay? For Jupiter is about 5.2 astronomical units on average. 5 times 120, it's a little over 600 million kilometers on average, okay? Now, you cube that number, you don't square it, you cube it, meaning you multiply it by itself 3 times. For the case of the Earth, it's 1 times 1 times 1, which is 1 still. For the case of Jupiter, you cube it, you take 5 times 5 times 5. 5 times 5 is 25, times 5 is 125. Don't forget that change in there because there is a 0.2 in it, okay? So it's gonna be about 100 and something, okay? More than 125 anyway. Here is the thing, what he found. Thus, the ratio is always the same for all of the planets. It's actually equal to 1 if you count the period in years and the distance in astronomical units. It's always 1. So this is odd. So if I know the period it takes for a planet to go once around the sun, all I have to do is monitor it until it moves at least 1 arc minute or arc 1 degree, okay? Then multiply that by 360, and now I know how long it takes to go once around the sun. So if I know the period, watch it, now it's in here. Wait for it until it moves 1 degree. Wait, oh, it took this long to go 1 degree. Multiply that number by 360, and now you know how long it takes to go once around the sun, roughly, okay? I'm just giving you a rough idea on how you can do it, okay? Because those planets, they move extremely, you have to really do very meticulous measurements to really find how long it takes. If I know the period, then I know how far the planet is from the sun, period, end of the story. That's what the third law is. All I have to do is take the cubic root of the square of that period, and vice versa. If I know the distance from the sun of a given planet, all I have to do is take the square root of the cube of that distance. That is what the third law is of Kepler. We're in great shape. 1664 hit. Actually, before that, Mr. Galileo actually took a toy and he started looking and monitoring objects in the sky, because this idea, so Mr. Kepler received a lot of resistance. First of all, the idea of having the the heavens not spherical, not symmetrical was an issue. And then the fact that the Earth is rotating around the sun, that was a big issue because we're no longer the center of the universe, we're no longer the center of the solar system. So that was a problem. So there are so many issues that were people basically were disputing with the theory of Mr. Kepler and Mr. Copernicus based on the data of Mr. Tycho Brahe. So what Mr. Galileo did, actually, he did something amazing. He took a toy. At that time, people used to play with it, and he modified it, and he pointed to the moon. What he saw there are valleys and mountains and hills in the moon, similar to what is going on Earth. So the idea that the Earth is actually part of the the reason why it has these things is because of man's sin. So what's going on with the moon? So that's a problem. The other thing also that he did, and he did a lot of other observations, including the Venus eclipses, phases. He looked at the Jupiter, and he immediately saw 3 objects going around it, 3 moons going around it. The next night, he actually saw the 4th one. He saw what he saw first of all Ganymede, Callisto, Europa on first night. The next night, he saw the closest moon to Jupiter, which is Io. Io, if you're looking straight at Jupiter, can be either behind Jupiter or in front of Jupiter, and it's hard to see, okay? Unless it's on one side or the other of Jupiter, then you can see it. That's really the problem with it. It takes about 42 hours to go around Jupiter, so it moves fast, okay? And this is for those sitting in Astronomy 125, this is going to be one of our experiments. And we're going to focus on Io specifically to try to measure the mass of Jupiter. That's really what the thing is. Now, he saw 4 moons of Jupiter revolving not on Earth. They don't go around Earth, but they go around another object out there in the sky named Jupiter. So this basically threw completely off the argument that the Earth is the center of the solar system, because, okay, if you don't believe me, here is a telescope, look at Jupiter, and you will see these 4 tiny moons that you couldn't see, and those moons must be revolving around another object outside of the solar system. I'm sorry, of the Earth, okay? So the argument that the Earth is the center of the solar system is no longer true, because here is an object out there, namely Jupiter. Here are 4 objects out there that go around Jupiter, and they don't go around the Earth. So now we don't have any question about the fact that the Earth is not necessarily the center of the solar system. So that was the argument that Mr. Galileo has presented. Okay, he did something else also for Saturn, but it was a little bit confusing for him. And when he drew it, he didn't understand what's going on. When he looked at Saturn, he saw what looks like 2 ears coming from its side. So he didn't know how, actually, when he drew it, that's how he drew it. He didn't know that that's actually a part of its ring system, okay? For Saturn, that is, but for Jupiter, it was a glitchy. Now, forward to the year 1664, London was hit by plague. And everybody, all the students were sent home, including one of them, college student, was Mr. Newton. Mr. Newton at that time, although he was still in college, he came up with 3 laws of mechanics. The first law of mechanics is just a phrase of what Mr. Galileo did, in a sense that objects moving in one direction, under no forces, will continue to move in the same direction with the same speed, as long as they are not subject to any forces. The second law says that basically if an object is subject to a force, that object will accelerate in such a way that the acceleration is proportional to the force and inversely proportional to its mass or inertia. The third law that he came up with, it says basically that if you push on an object, the object will push back. It's called the action and reaction principle. So he came up with 3 laws, and those 3 laws, they seem to fit and explain everything we know in our daily experience. When the plague hit, I forgot the name of the person who came into him and told him, listen, this is what Mr. Kepler came up with. He came up with 3 perfect laws that describe the behavior of the objects in the sky. the first law that the path of those objects must be elliptical and the sun is in one of the focal points. The second law of Kepler said that basically those planets sweep equal areas at equal times. And the third law says that the square of the period is proportional to the cube of the semi-major axis, basically how far they are from the sun. Okay, so these are the three laws. Can you explain them in light of your three laws of motion? So what he did for about 40 years, the plague when it hit London, it lasted almost the same time as how much COVID is doing for us now. So he came up with an explanation of these three laws. And one of the consequences he came up with is the universal law of gravity. Okay. And this is important. This is part of what we learn in astronomy that is going to be very helpful for us, the scientific method. Because here is the thing. If all Mr. Newton did was to explain what Kepler's laws are, that is not good enough. That is not, it does not elevate that theory than any other theory that you can come up with, anything at all. You could say, okay, there are angels in there moving all of the planets so that the three laws of Kepler work, and that is perfectly legitimate. You could come up with any interpretation that you can come up with. Because if all you do is explain what has been observed experimentally, that is not good. So this is the takeaway from it. Mr. Newton did that. He explained what Mr. Kepler has seen with his laws. That is not good enough, Mr. Newton. You need to come up with something better. You need to tell us something that we didn't know before. Your theory needs to predict things that we couldn't see before. This is exactly what Mr. Newton did. He was able to find that constant of proportionality. Remember, the ratio of the square of the period over the cube of the distance is fixed. He says that the mass of the sun. Okay, that sounds to be good. Can we test it with something else? It works with the Earth and the Moon. So instead of putting the Moon mass, you're going to the Earth mass, the Sun's mass. You're going to put the Earth mass for the case of the Moon around the Earth. That seems to work. That is actually what works also for Jupiter. If I were to find the period, how long it takes for Io to go around Jupiter, and if I know the distance for Io, how far it is from Jupiter, based on how many radii, if you wish, of Jupiter, how big the Jupiter is versus how far it is from how Io far is it from it. So I know how far it is just by looking, and I know how long it takes just by documenting the time. Then that gives me measurement for the mass of Jupiter. This is exactly the lab that we're going to be doing in Astronomy 125. I'm just describing the lab into how to measure the mass of Jupiter by doing this same stuff that Mr. Newton basically has shown. Okay, there was some more stuff in Mr. Newton's work than that. I mean, one of the things is the satellites out there that are being deployed in there, so they rely on Newton's mechanics. And Newton's mechanics, based on his mechanics, explaining Kepler's laws, works beautifully for all the planets. And I'm going to start naming them, each and every one of them. I'm not going to miss one of them. The first planet that is beautiful and works perfect for it is not Mercury, but Venus. Then Earth, Mars, Jupiter, Saturn. At that time, they were known. Okay. Later on, when the planet Uranus was discovered by Herschel, the same laws, these same laws of Newton were used to find where Neptune is. So Neptune was not known at that time. There were problems with the path of Uranus. So they took those numbers, those laws, and they said, okay, in order to fix the problems of the path of Uranus, we need another planet, and here where it needs to be. Sure enough, they went there and found Neptune. So in other words, a theory needs to go a step further. I skipped Mercury in purpose. Mercury, it failed for it. Newton's laws did not work for it. Does this mean that Newton's is wrong? Absolutely is wrong. His law, his theory is not good. That is really the whole point of it. If a law works a million times, a billion times, if you wish, and it fails once, you need something else. That's exactly what happened with Mr. Newton. He explained everything that he can think of at that time. He even predicted things that did not exist and they existed. Halley's comet, for example, came in, and then Mr. Halley, based on Newton's laws of motion, based on his interpretation of Kepler's laws, he was able to predict exactly when that comet is going to appear again, 76 years after that with a few days. And he said, that's when it's going to show up. Sure enough, after he's long dead and Mr. Newton was dead, that comet came back, and now it's named after him, Halley's comet. So where is that coming from? Newton's work that is an extension of Kepler's laws. But it failed with Mercury, so it's no good. That's when Mr. Einstein came in. He came up with a theory of the law of relativity, general theory of relativity. What Mr. Einstein did was explain everything that Mr. Newton has done. In other words, everything that Mr. Newton has done needed to also stay intact. In addition to it is to explain Mercury. But if that's all Mr. Einstein did, that is not good enough from him too. Sorry, you have to do better. You have to predict something that did not exist before in order to be accepted. So if all of the things that Mr. Einstein did was to maintain the work of Newton and add to its justification now for Mercury, if that's all you do, that is again explaining what we know. We need something more, something predicted that we did not exist. One of the things that Mr. Einstein predicted was the gravitational lensing. This sounded strange. What in the world are you talking about? Gravity acts as a lens. Sure enough, about 10 years, about 40 years after his theory was published, when during the solar eclipse, the sun bent the light coming from the stars behind it. And now his theory, at least now, predicts something that can be measured. It predicted a lot of other things too. Predicted neutron stars, predicted black holes, predicted other things. The GPS system that we use today is actually based on Einstein's work of general theory of gravity. So now, basically, you see where I'm headed with this one. Science, in order to really be accepted, you cannot just explain things that has been observed. You have to go a step further. So this is how the scientific method works. I know I have given a lot of introduction. It's almost half an hour introduction of the unit. So let me go into it, delve into it, and let me share the unit itself. I know I gave you a lot of background, a lot of history behind it, but that's hopefully it's useful enough. Again, this is not a replacement for what you guys are supposed to be doing, which is to go and read the units, okay, and do the problems and the quizzes and everything, and understand them hopefully. And if you have any difficulty, please let me know. Again, this is Tycho Brahe, Kepler, and Galileo's contribution into astronomy. Then we talk about the ellipse in here, which is part of the things that we're relying on, trying to understand what's going on with the path of the planets, and the three laws of Kepler, and discuss how what Mr. Galileo did when he observed it. Okay, I can actually go to the notes in here, and what Mr. Tycho Brahe in here did. He again did not have access to a telescope. He was using really with a visual, and he was relaying the data. Okay. Mr. Kepler came up with this laws. Okay, so let me explain what the ellipse look like. I mean, it has a picture here. So if you want to make it at home, you need 2 pins. Those are your focal points. They never change. You take a string. In class, we used to make it when we were live. Okay. You take a string. It's not really hard to do, honestly. You take a string and make it loose. So you connect it loosely. You don't tie it to the pin. So if we're going to make it, don't tie it, okay? Just take a string and wrap it around and tie it, and make sure when you hold it between the pins, it's loose. There is a loose end to it so that you can run a pencil. And now you draw the pencil. How long this path is never going to change because the string doesn't stretch. So the distance from this point that you guys are seeing in here is this point. And if I take this point, it's going to run this way. If I take this point, it's going to run this way. If I take this point, it's going to run this way. No matter how you look at it, this distance never changes because it's the distance between the two focal points, and they're fixed. They're nailed, actually. You use nails to fix them. It's this distance that changes and this distance that changes, but the combination never changes. The sum never changes. So this plus this is the same as this plus that. It's the same as this plus this, and so on and so forth. So an ellipse is the sum of all the points that are equidistant from the two points in this case. Okay, so those are some of the interesting properties of an ellipse. So let me stop sharing and actually go into my notes in here. So again, I need two focal points. So these are the two focal points, and the assembly of all the points that are equidistant from them. So any points in here, this one in here, for example, the distance between that and the 2 points is the sum of these two lines. Okay. In his theory, he says the sun occupies one of the two focal points. I'm exaggerating in here. For any planet in here, with the exception probably of Jupiter, the two focal points are inside the sun because the sun is huge, okay, compared to the planets. So the sun will wobble a little because of this, but not that much because of that. Because as the planet is on this side, the sun will move slightly to the other side so that the very center is actually where the rotation is, okay? So the sun will move around the very center in here, okay? But that's negligible motion compared to the motion of the planets. So this is the planet, and the path is an elliptical path. So what is an ellipse again? It's the ensemble of these points in here. This distance from here to here is called the major axis. So this is from the furthest point to the furthest point. Okay. This distance from here to here on the flat side is called the minor axis. Minor axis. The distance between the focal points is actually the focal distance. Okay, that's sorry. And half of that, half of the major axis is called the semi-major axis. So this is half of that. And half of the minor axis is called actually the semi-minor axis. I mean, this is hopefully self-explanatory. The distance between the center of symmetry, in this case, this point where the two axes meet, and this point is actually where the focal distance is. Okay, so the focal distance is actually the distance of a given point. It is the same, okay, by symmetry, it's this one or the other one. Okay, the letters that you will see everywhere you're going to look at this one in here, and it's in the book too. So this is usually the letter A. This is usually the letter B. And this is usually the letter C. In other words, the major axis itself is equal to 2A, because from here to here is A. That's semi-major axis. Twice A is the actual major axis. And the minor axis, how big it is actually 2B. And the distance between a focal point and the focal points are separated by 2C. Because each one is at one C on one side and the other one is a C on the other side. So 2C is how far they are. So this is basically how the ellipse is. Okay, so this is how the path of the planets are. They are all through the ellipses, where the sun, so the first law of Kepler, it says that the planets orbit the sun in elliptical paths where the sun is located in one of the focal points. Again, which one, it doesn't matter. They can choose, okay? It's the same. Okay, this could be this one or the other one, doesn't matter. If it's on this one and the Earth happened to be on this one, so we are in the perihelion. But if you are in here, we are at the aphelion, so we're on the opposite side. That's all. Okay. That's one thing. The other law in here is that if you take a planet, this is where the focal point is, and this is the planet. And imagine a line, imagine it, doesn't exist, okay? And wait for a certain period of time, that planet will move in here. So it's no longer here, it's in there. This area in here is swept by that imaginary line during that time. So this is a given time, okay? Given, a week, 2 weeks, a month, whatever you decide to be. And when it's further away, it's actually was here, and now it moves to here. Okay, so it was here, and now it's in here. So this area is also swept, but it's a longer now imaginary line. So the arc in here that it covers is less than this arc when it's close by the sun. But the area is the same. This area 1 is the same as area 2. They're the same area. So it doesn't matter as long as it's the same given time. Same given time. In other words, if you wait 2 weeks in here, you better wait 2 weeks in here. If you wait a month in here, you better wait a month in here. It doesn't matter how long it is. So the second law of Kepler says the following. Planets sweep equal areas in equal amounts of time. Okay, again, I'm describing Kepler's laws in here, okay? The third law took him a little bit of time to figure out, okay? This is based on Tycho Brahe's observations, okay, so that you guys understand. So there is a connection. Tycho Brahe spent all of his life basically collecting this data and making it ready for Mr. Kepler to do the math, okay? So after that came the third law, and the third law is the following. So if I take again the sun somewhere in here in the focal point, and if I take path in here, I should probably use a tool in here. Hold on, can I do the tool? Hold on, Control Z. I use this tool instead. Draw an ellipse. There is an ellipse. I'm going to exaggerate this ellipse to make it a little bit more elongated, because we're going to come to a quantity that is of interest to us. So let me go back into my drawing tool. So this is the path, okay? So this is an ellipse. So the planet, if you start from here and you wait until it goes a complete cycle, it comes back, that is a period. So the period is the time it takes to complete one cycle. For Earth, it's 1 year. Okay. If I take this distance and this distance, that is 2a, by the way. Because remember, A, if I take the axis of symmetry, that is this distance and this distance. So this is 2a. From here to here, from the most extremes, that's 2a. Half of that is a. So the semi-major axis is the average distance to the sun. In other words, for the case of the Earth can go as far as 153 million kilometers or 147 million kilometers. So if I take 153 and add to it 147, that is 2a. So the 0 plus, that's 10, 5 plus 9 plus 1, that's another 10. That's 300 million kilometers, not 300 kilometers, 300 million kilometers. So that's the major axis. I have to divide that by 2 in order to find the semi-major axis. So for the Earth, on average, it's on a distance about 150 million kilometers. Which is, by definition, 1 astronomical unit. That's basically how far the Earth is from the sun on average, okay? Now, the third law says the following. So this period, P, which is a symbol for it is P, for Earth, it's 1 year. And this distance, which is the semi-major axis, or the average distance, it says that P squared is equal to A cubed, provided, the key in here, provided. So there is a big deal in here. Provided P is in Earth years, and A is in astronomical units. In other words, for Jupiter, for example, P is 12, okay? It's not exactly 12, but it's about 12, okay? For A, it's an astronomical unit. For Jupiter, for example, it's 5.2 astronomical units. So they're not going to give me that in kilometers. If you choose to have different units, this ratio is constant. That's basically in a nutshell what it is, okay? This ratio is constant. That's basically what this thing is. So this is the third law. The third law says that this is true for all the planets. So this is what the third law is. The square of the period is equal to the cube of the average distance, as long as P is in Earth years and A is in astronomical units. If you don't have that, convert them. In other words, make the conversion here, you can find the constant, what that constant is. It turns out that this ratio is actually the measure of the mass of the sun. Okay, that's how the sun was weighed. Actually, take any planet, you're going to find the same ratio, and there is without the g times and the 4 pi squared in it. That's a measurement of the strength, if you wish, of the mass of the sun. Okay, so this is basically the 3 laws of Kepler. I know the book goes in detail, so I'm hoping that you guys can go and make sure that you have them. So let me go into sharing again, unit 12. So now we have a description. Now there is a measure in here, which is how flat the surface is. In other words, how close the planet can get or how far it can get. That is called the eccentricity. So the eccentricity it really measures how far the 2 focal points are. If I have 2 focal points that are very close from each other, the ellipse would look very close from a circle. If the 2 focal points are far away, the ellipse is kind of open a little bit. So that is basically what this thing is. If the 2 focal points happen to be the same point, we're back to a circle again. So this is basically the idea behind it. So the circle has an eccentricity that is equal to 0. If this distance is very close from 1, meaning that it is as open as it can get. So this is as thin as I can get. This distance between the 2 focal points, because the eccentricity is equal to actually C over A. C, remember, is the distance between the 2 focal points. If the 2 focal points collapse on each other, they become 1 point. Then C is equal to 0. In that case, I have a circle. If the 2 points are as close as from the extremes, then in this case, C is very close from 1. So the value of the eccentricity is at best equal to 1, which is a line. that is not possible. That means the planet or the object would go straight into the sun. So it has to be less than 1 for a planet, for a physical planet. And at worst, it can be 0, as small as 0. For the case of the Earth, it's almost 0. Remember when we were talking last time about, or we're going to talk about this one in the future, actually, about the Milankovitch cycles. Sometimes the Earth path will be more eccentric than others. Sometimes, basically, sometimes it's going to be very close from the sun, and sometimes it's going to be very far from the sun. So that impacts the weather on the Earth. So in that case, the eccentricity of the Earth will move far away from 0. Not really that far, but it's relatively speaking is far. But nowadays, it's very close from 0. So its path, although I gave you the discrepancy between 153 and 147, it's still, because you're talking millions of kilometers versus 6 million kilometers, that is nothing, okay? So it's practically, the eccentricity is equal to 0. So it's practically, it's very close from a circle. That's why Mr. Copernicus and the people before him were really not far off, in a sense, from their calculations. But as for objects, for example, for Mars, Mars has a little bit of a high eccentricity, relatively speaking. So again, this is the path of the planets. And this is the first law. Again, I just put it earlier in there. This is the second law. I described it in terms of equal areas in equal times. I think you need a comma in here. Okay. And so it's the same period in here, 2 months. Okay. And the third law is the one that says p squared equal to a cubed. Remember, p has to do with the time in years. Okay, for this to hold true, and a is in astronomical units. Okay, p in years and a in astronomical units. Otherwise, you have to find the constant of proportionality, which has to do with the mass of the sun. I mentioned Mr. Galileo's basically contribution in here with the telescope. One of the things he did saw was the different phases of Jupiter, of Venus as it passes between the Earth and the sun, okay, as it rises and sets. So it goes through phases, okay? And then he found the craters on the moon showing that the moon was not a perfect sphere. So there are problems. So here is that issue of the theory that everything has to be known. And then he discovered the 4 moons of Jupiter. Now they bear his name. They're called actually the Galilean system. So all the 4 moons, Ganymede, Callisto, Io, and also Europa, they are actually named the Galilean system because he's the one who discovered them. Discovered the rings of Saturn, but he was confused of exactly what they were until later on they were identified as rings. Okay, and the sunspots also, that's one of the things that you observe with his device, okay? So really, he laid the foundation for a lot of these things. This is his notes in here for the moon and also for the different objects. For what? For the different moons of Jupiter. Okay, he had actually a drawing that is not included in here for the years of Saturn. And this is basically Venus's cycle as it goes around the sun. Okay, so this concludes this unit. You have homework problems. We still have about half an hour maybe to discuss them. So let me share with you guys the problems. Let me first of all find them, locate them on my screen. Okay. Share. So this is week 3. So we have just finished basically going through this unit. So I'm hoping that you guys are doing the reading, making sure you do the problem. You have these 2 homework assignments that are due next weekend. You have also a quiz that is due next weekend. The recording of this session is going to go here again, next to the one that was recorded from Monday. The homework assignments, they're here. Here is what I believe the homework is. There's tremendous value for you guys. You need to do them. If you struggle with them or you don't know how to do them, please let me know, okay? These are from units 7, 8, and 9, so the previous units that we covered, not this one's in here. It's asking you, what is the phase of the moon during the total solar eclipse? If you go through your notes, you'll see exactly when the moon basically blocks the sun. It has to be during daytime, so it cannot be during nighttime because you have to block the sun. It cannot be during nighttime. And when is the lunar eclipse? And you need to have the entire moon block be blocked by the Earth. Okay. And why don't we have a lunar and solar eclipse every month? And it has to do with that tilt of the path of the moon around the Earth versus how the Earth is going around the sun, meaning the virtual position of the sun on that path. Okay, and there is a 5 degree, and sometimes it has to be within 1 degree to see that. Okay, why again, this is not to challenge you guys. This is not an exam. So you're supposed to know how to do these things. If you struggle with them, please let me know. We can go through them, talk to your peers, work together, and come up with a good solution to them. So this is not an exam. The only condition I have for you guys, if you're going to be working with your peers, is to include their names in your assignments, in your submission. Okay. And then why does the moon look red during a total lunar eclipse? So it's not completely covered. So there is the rays of the sun that graze the Earth. So that's basically what's going on. And then you have these two problems. Each and every one of them is worth 10 points. So the first one in here show that the ratio of the moon's diameter to the sun's diameter is very similar to the ratio of the moon's distance from the Earth to the sun's distance from the Earth. Sizes and distances needed to solve this are in appendix table T1, table 1, and also 7. And here is table 1, and here is table 7. So really, if you don't have the book, you should be able to do this once in here too. So table 1 in here, it gives you some critical pieces of information. So what we need in here, can I write in here? No, I can't. Can I scribble in here? What is that thing there that said that it could do that? I don't see it. Okay, anyway. So the point in here, what is given for you, what you need in here? You need the sun's diameter. Okay, so I need to find where the sun's diameter is. And if I look carefully in here, it should give me velocity of light, gravitational constant, Planck's constant, mass of hydrogen, mass of electron, Stefan-Boltzmann constant, Wien's law constant. And then we have the astronomical unit. The astronomical unit, actually, we need it because it's the distance to the sun. The moon's diameter to the sun's diameter is very similar to the moon's distance to the Earth distance to the sun. So we need the Earth distance to the sun. So this is a number we will need. Okay. 150 million kilometers. That's basically what I'm putting it in here. Okay. It's 1.495978706. That's how precise it is. Times 10 to the power 11. So if you want to, you can approximate 250 million kilometers. So you need, and that is part of the question, Earth to the sun's distance from Earth, okay? And then, I mean, the sun's distance from the Earth, that is 150 million kilometers. We need the moon's distance though, because the moon's distance from the Earth is also needed. And that is actually here. If you look at the table 7, it says the moon is at a distance, at a distance of 384,000.4 kilometers from the Earth. Distance from planet, and the planet in this case is Earth, and the moon is our moon. I mean, if you look at Phobos, for example, it's at 9,380 kilometers from Mars. That's how you read this table. The distance from planet, in this case Mars, to Deimos is 23.5 times 1,000. Remember, don't forget you have 10 to the power 3 kilometers. So it's 23,500. So in other words, Phobos is less than half the distance from Mars than what Deimos is. So those are the two moons of Mars. We don't care about them. We care only about our moon for this particular problem. Okay. 384,400 kilometers, how far the moon is from the Earth. And then we need how far the sun is from the Earth. That is 150 million kilometers. Okay. It's a good idea to retain everything in the same units. Here it's given in meters. Here it's given in kilometers. So I have to stick to the same thing, which is kilometers in this case. So that apples compared to apples. And then the sun's diameter, I need the sun's diameter. What is the sun's diameter? So I will keep on continuing. The light year, the parsec, the year, mass of the sun. We don't care about that, but we need its radius. Its radius is 6.96 times 10 to the power 8 meters, or 696,000 kilometers, roughly 700,000 kilometers. 6.96 is almost 7. So it's about 700,000 kilometers. That's how big the sun is in radius. And the radius of the moon on the other table is 1,738 kilometers. So I need everything in kilometers. This is in meters, and this one is in kilometers, so I have to have them in the same unit. So let me share with you the other one in here. Share. Okay. Actually, probably, yeah, let's write it in here. So this is problem one, I'm sorry, from part 2, because it has 2 parts in there. Okay. So what we have in here, we have the radius of the sun is 700,000 kilometers. I know 696,000 kilometers. The radius of the moon is 1,738 kilometers. Okay, I could say it's roughly 1,700 kilometers, so that we make life easier. The distance Earth-Sun is about 150 million kilometers. The distance from the Earth to the moon is 384,400 kilometers. Again, if I read the question carefully, it says in here, show that the ratio of the moon's diameter to the sun's diameter is very similar to the ratio of the moon's distance to the Earth distance from the sun. So again, so the Earth, the radius of the moon, which is 1,738, divided by the sun's radius, which is 700,000. You're supposed to check this ratio and also check the ratio of the distance to the moon, which is 384,400 kilometers, divided by 150 million kilometers. You're supposed to check this ratio and see that the two are very close from each other. That's basically what this question is. Okay. Next question. It says a total solar eclipse occurs over Africa on August 2nd. Remember that slide from Unit 8? It has the different ones in there. Based on the 6,585. So again, if you have difficulty finding it, please let me know. Day, 8-hour time, repetitions of similar eclipses. When and where will the next solar eclipse, total eclipse, happen? Okay, here is the thing. First of all, the where. Okay. I have so many days, 6,585 days and 8 hours. So wherever it's in Africa, North Africa, actually. So let me write these numbers in here, 6,585 in 8 days. Can I copy these 2 things? It's probably good. Copy, because we need them in the other one. And in here, share. Maybe it's going to come in not the same color. Let's see. Paste. Let's see if I can select them all and change the font color. Okay, that's better. Okay, so that's all we need for it now. So the eclipse in North Africa is on August 2nd, 2027. And we're going to add to it 6,585 days in 8 hours. Here's the trick with the 8 hours, okay? We know the line that passes through that line where the eclipse was supposed to be, that is actually Greenwich time, okay? So that is the 0 hour. 8 hours later, we'll put it on this side of the Earth, 8 hours later. If you check, you will see that the west coast we are on is actually at 8 hours later. So the answer to the where is going to be somewhere in the west coast, anywhere from Alaska all the way to Mexico, to all of this time zone. Okay, so that is the where. Now we need to know when. It says 6,585 cycle when the next one is. So we know the where is going to be somewhere in here. Okay, okay. As a matter of fact, it's going to be somewhere anywhere between this side of the United States and Mexico, the west coast of Mexico. So the when is that going to happen? Well, 6,585 days is how many years that is. Remember, a year is 365 days, okay? And the starting point is on this date, which is August 2nd. So I need to take 6,585 and divide it by 365. So if I put it on a calculator, okay, 6,585 divided by 365. That's how many days in a year, okay? And it's giving me 18 years point something, okay? It's giving me 18 years on some change. 18 years and some change, okay? I don't care about the change right now, we're gonna find it, okay? So what I want to do is do this. I want to know what is that difference? So what I do in this case, take 365 and multiplies them by 18 years, because I know I need 6,585. And I just said that it's 18 years or some change. So I need to find that number of days really, which is the change, okay? Because we want to make a prediction. So what I say in this case is take 365 times 18. That is going to be a, let me get a calculator on my screen. So if I multiply this 2, which is 365 times 18, 6,570. So this product is 6,570. 6,570. As I was saying, the difference between 6,585 and 6,570 is 15 days. Okay, you have to be very careful in here. Why? Because some years are not 365, they're 366 from this date. So you'll be tempted to say, okay, from 2027, all I have to do is add to it 18 years, and 8 plus 7 is what, 15, and 2 plus 1 plus 1, that's 4. So it's going to be in the year 2045. That's correct. But which day that is, that's the key. So you don't just go on August 2nd, 2045, and add to him 15 days, because remember, 18 years exactly would put it at 2045 on that date. But it's not quite right because you have leap years. So from 2027, the next year is 2028. This year is actually a leap year. Then 2029, then 2030, then 2031, then 2032. That is also a leap year too. Okay. Then after that, 2033, 2034, 2035, and the year 2036 is also a leap year. So there is an extra day in here that needs to be consumed from the 15 days, and there is an extra day that needs to be consumed in here from the 15 days, and there is an extra day that needs to be consumed from the 15 days. So in here I would be left only with 14 days from that difference, basically. And in here I would be left with 13 days after I consume the other day for this leap year. And in here I would be left with 12 days from that leap year. Still not over. So we need to go to 2037, which is a normal year, 2038, 2039, and then 2040 is also a leap year. That too will consume another day in here, and we'll be left with 11 days from that difference. Remember, the difference between 18 times 365 is 6,570, but we actually have to do 6,585, so we have a difference of 15 days. And each time we hit a leap year, we have to consume one of those extra days. So again, 2041 is a normal year, 2042 is a normal year, 2043 is a normal year, 2044 is actually also a leap year. So that will leave us with just 10 days in addition to that. The next year is a normal year, 2045, when we predict the eclipse is going to happen. So we have to go to this day and add to it 10 days for a total of August 12th, 2045, when the next lunar eclipse will happen, and it's going to happen in North America about 8 hours after the Greenwich time, which will put us in the Pacific region. Okay, I hope that this problem makes sense to you guys and you know how to do them. The other problems, oh man, we're running out of time. let me quickly share with you guys so that we can have an understanding on how they look like. No, that's not the one. Yeah, that's the one. Let me go and share. Share. So let me share the next assignment. Again, you are supposed to do all of this. It will only help you understand the materials better. Again, it's a great assignment, so you better do it. But then also make sure that you understand what you're doing. And I don't want you to be struggling with it. I really want you to do them and do them right. So if in case you struggle with them, please let me know and we will do them together so that you have a full understanding. That's the purpose of this assignment. It's not to challenge, it's not a test, in other words. Okay. So again, each question is worth 5 points, okay, for a total of 20 points in here. The smallest separation between the Earth and Jupiter is 588 million kilometers, while the largest separation is 968 million kilometers, okay? It's basically about 4 astronomical units to about 9 astronomical units. No, it's about, what, 6? Yeah, 6 astronomical units. 6 times 150 is about 900, okay? Given that Jupiter has a physical diameter, this is the diameter of Jupiter. Its radius is about 70,000 kilometers. Its diameter is about 140,000 kilometers. What are the largest and the smallest angular separation? All you have to do in this case is, because remember that law that we saw last time, actually from unit, I think 9. Basically, all you have to do is take L, which is the size of the object. In this case, it's 140 million kilometers, divided by the 2 pi times the distance, which is 258. So you have to multiply that by 2 pi. And that is going to be the angular separation, okay, in degrees. So you have to multiply that actually by 360 to find it in degrees. So again, the formula that we're going to be using for almost all of these problems, and let me show you what that is, okay? Let me stop sharing this screen. Share, and this one. So here is the formula that we're going to be using for those questions. You have the size of the object as seen from here. So this is Jupiter at some points, and some other points Jupiter is going to be very far. Okay, that's basically the bottom line in here. Obviously, this is going to appear a little smaller when it's far, but that's the point of it. So you know this distance, and later on when it's far away, it's a different distance. And you know the size of Jupiter is not going to change. It's the same size. So what you're saying, this L over 2 pi times the distance is equal to the angle that is sustaining the size of the object, okay? And in the second case, it's actually this angle, okay? Divided by 360. So you're supposed to find this angle in degrees, that's all. So you have to find the angle in degrees is equal to 360 degrees times the size of the object, which is 140,000, for Jupiter doesn't change, divided by 2 pi times the distance. The distance changes. Sometimes it's 588 million, and sometimes it's 968 million. And that is the whole problem of it, is to find how big Jupiter's size is going to be when you look at it with your eye or with a telescope. As long as it's close by, it's going to appear bigger. When it's further away, it's going to appear smaller. And that's the bottom line, okay? So this is the angular size from this question. And this is actually true for question 1, for also question 3, which is problem 12, a cloud appears, so we're given the degrees and all of that. And also for question 4, namely Andromeda Galaxy. They give you the size, they give you the angles, and you're supposed to find how far they are or something else. So they're all the same formula. The second one is slightly different though. And let me stop sharing and share with you problems. So again, here for 3, for the Andromeda Galaxy, M31 is similar to our galaxy. The diameter of the galaxy is 140,000 light years, not kilometers. Okay, you have to be careful in here. It's a light year. But from our perspective, it occupies only 3.18 degrees, which is actually much bigger than the moon, if you can see it on a clear night. How far Andromeda is? Again, use that formula. Again, you have L, which is the size of Andromeda, which is 140,000 light years, divided by 2 pi times the distance. You don't know what the distance is. You want to find what the distance is, but you're given the angle, which is 3.18 divided by 360. So you have everything. You should be able to find the distance. So again, Let me share with you this the other screen. For the case of Andromeda, you want to find D here. You don't know what D is. So you say here D is equal to the size of Andromeda, which is 140,000 light years, okay, divided by 2 pi times 360 degrees divided by the size of the Andromeda. So from here, plug in the numbers, and you should be able to find how far away Andromeda is from our point. It doesn't matter, from Earth, the Sun, the Moon, the next star, or the entire galaxy is the same thing. Because, I mean, it matters a little bit if you're one side of the galaxy or to the other, because our galaxy is about 100,000 one way or the other. Okay. Then the cloud also is similar. You're given degree and angle. From the weather reports, it shows that the cloud has an altitude. So you're given D, and you want to find the L. So in this case, it's the same formula, except you want to find where the other. So now you want to know L. For the first problem, you're given L. For the last problem, you're given L. For the first problem, you are given D, but you were supposed to find what alpha is. For the last problem, you're given alpha, but you're supposed to find what the D is. For this problem, actually, you're given alpha. I mean, yes, you're given alpha, which is for the clouds. What is the cloud? Alpha is 10 degrees, and also the distance, but you don't know what the size of the cloud is. So you're supposed to find what the size of the cloud is. So it's the same formula. Again, if you struggle with this, please let me know. Now, here is another one. Suppose you are an alien living on a fictitious planet, and you want to measure its size. The sun is shining directly down a missile 1,000 miles to your south, while at your location is making 36 degrees from straight ahead. What is the circumference of this planet or this moon? And then what is its radius? So once you find the circumference, all you have to do is divide it by 2 pi, and you find its radius. So what we know, 1,000 miles down the road, the shadow makes 36 degrees. In our location, there is no shadow. So let's look at it. Share. This is similar to what Mr. Eratosthenes determined the size of the Earth. So again, here is this location and this location, that's 1,000 miles. Here, there is no shadow, 0 degree shadow. Here, it's making 36 degrees shadow. So in other words, 36 degrees, not 360, okay? Here, this line and this line, this is basically what the rays of the sun are. And this is how much degree is an opening, which is exactly this same angle, 36 degrees. So what you say in this case is, look, if I go full circle, which is 360 degrees, that gives me the circumference, which is 2 pi times the diameter, or the C, the circumference of the planet. But if I go only 36 degrees, I only describe 1,000 kilometers, 1,000 miles. Okay, that's the unit in here. So in this case, the ratio of the circumference over the ratio of the arc distance, which is this distance of 1,000, is the same ratio of the two angles. So 36 or 360 divided by 36 is the same ratio of C over 1,000, and this ratio is 10. So the circumference is 10,000 kilometers. All you have to do is multiply 1,000 by 10, and you get 10,000 kilometers. What is its radius? Radius is equal to the circumference divided by 2 pi. So it's going to be 10,000 divided by 2 pi, which should give you a number, what, 10 divided by 12 by 6 is 1 point something, 1.6 or 1.5 something, okay? Slightly over 1,500 kilometers. So again, this is how you answer these questions. If you have any difficulty with these things, please let me know. I really don't want you to struggle. I don't want you to even think twice about them, but I want you to do them. I want you to really be at ease with these things, because this is part of your learning process. And doing them will reinforce all of these ideas that we learned, and basically will give you a different perspective to it, so that you guys can master these things. Sounds good? Okay, so I'm going to stop the recording right now, and I will see you guys next week. Okay, remember, next week there will be plenty of assignments also. And we're hoping to have our midterm sometime, not next week, but the week after. Bye.